Let me ask you something. What do you think happens when something falls into a black hole? Go ahead, think about it for a second. If you said it gets crushed, wrong. If you said it gets destroyed, wrong. If you said it disappears forever, wrong. And if you said Stephen Hawking told me it gets erased from the universe, well, Stephen was wrong too. And I spent 28 years of my life proving it. Now, I'm going to tell you several things in the next 30 minutes that are going to sound completely insane. And by the end, I want you to understand not just what is true about black holes, but why everything you've been told is wrong and what the actual truth turns out to be. And because the truth is stranger than anything you've ever heard, I promise you that. It started for me at a dinner party in San Francisco. Stephen Hawking, who at this point is already the most famous physicist in the world, gives this little informal talk to a room full of physicists. And he says very calmly, as if he's telling us what the weather is like outside, that when something falls into a black hole, the information it contains is permanently, irreversibly destroyed, gone. And it's not relocated, not hidden, destroyed. Now, you have to understand what information means here. I don't mean your emails, I don't mean the words in a book. I mean the fundamental physical description of everything. It's every atom, every particle, every quantum state that makes up whatever falls in. All of it, according to Stephen, is erased from the universe forever. And the black hole swallows it, and then eventually the black hole evaporates. Hawking had figured out that black holes radiate and slowly disappear. And when it's gone, that information is just nowhere. I sat there listening to this, and I felt my stomach drop. Because here's the thing. And what Hawking was describing, if it was true, would be the most profound violation of the laws of physics ever discovered. It would break quantum mechanics at a fundamental level. And the rules of quantum mechanics say, and I mean this as an absolute non-negotiable law, that information can never be destroyed. It can be scrambled, it can be hidden, but it cannot cease to exist. So either quantum mechanics is wrong or Hawking was wrong. I looked around the room at the other physicists and nobody was saying anything. Some of them were nodding. And I thought, am I the only one who sees how crazy this is? I went home that night and I started working on it. I didn't stop for 28 years. So let me tell you what a black hole actually is. Because most people have it completely wrong from the start. A black hole is not a hole. It's not really even black in the deepest sense. A black hole is a region of space where gravity is so incredibly strong that nothing, not matter, not light, nothing, can escape once it crosses a certain boundary. And that boundary is called the event horizon. Now here's the first thing people get wrong. From the outside, if you're watching someone fall into a black hole, they don't just disappear, they slow down. Hence, they freeze, and they get redder and dimmer as the light from them gets stretched by gravity. To you, the outside observer, they never actually cross the horizon. They appear to hover there forever. Hence, but from their perspective, from the perspective of the poor person falling in, nothing special happens at the horizon. They cross it, they don't feel a thing. And the laws of gravity say the horizon is not a special place. There's no wall there, no fire, no warning sign. Hence, if you're falling into a big enough black hole, you'd cross the event horizon and not even know it, not immediately, not for a while. Two completely different experiences of the same event. That's already weird, right? But wait, it gets weirder. Here's what Hawking figured out in 1974, and this part is absolutely correct and brilliant. Black holes are not truly black, they radiate. Quantum mechanics, when applied near the event horizon, predicts that particle-antiparticle pairs are constantly being created just outside the horizon. One particle falls in, one escapes, and the escaping particle carries away a tiny bit of energy. Over an enormous amount of time, we're talking longer than the current age of the universe for a stellar black hole. The black hole loses mass and eventually evaporates completely. And that radiation is called Hawking radiation. Here's the problem, and this is where Hawking went off the rails. He calculated that this Hawking radiation is perfectly random, and it carries no information about what fell into the black hole. It's thermal noise, pure and simple. So by the time the black hole has completely evaporated, where is the information? According to Hawking, nowhere, gone. Think of it this way. Imagine you have a book. Let's say it's a copy of the New York City phone book from 1965. Your father's name is in there. You throw it into a fire. Okay, the paper burns, the ink burns, but in principle, if you had a perfect physics simulation, you could track every single molecule of smoke and ash and heat, and you could theoretically reconstruct a book. The information isn't gone, it's just scrambled, totally scrambled, but not gone. Now, imagine a fire that when the book burns, the smoke and heat that come out carry zero information about the book, not scrambled, truly zero, nothing. That's what Hawking was claiming black holes do, and I'm telling you, that violates everything we know about how the universe works. And quantum mechanics says you can always, in principle, run time backwards. Every process is reversible. If you know everything about the final state of a system, you can reconstruct the initial state. It's a fundamental symmetry of nature. Time is reversible at the quantum level. Information destruction breaks that symmetry. If information can be destroyed, you can't run the clock backwards. Hence, the universe becomes fundamentally irreversible. And that, my friends, would be a catastrophe for physics as we know it. So there were basically three options on the table. Option one, Hawking is right. Information is destroyed, and quantum mechanics has to be fundamentally modified. This was Hawking's position. Option two, information somehow escapes from the black hole and the Hawking radiation, but in such a subtle scrambled form that Hawking's calculation missed it. This was my position, and the position of most quantum field theorists. Option three, some completely new physics comes in at the very end when the black hole is almost evaporated. Some kind of remnant that holds all the information. Hence, the problem with option three is that it leads to absolute nonsense. You'd need to pack an effectively infinite amount of information into a tiny little object, and that creates all kinds of problems. So the fight was really between Hawking and me, and most of the theoretical physics community was genuinely divided. Now, here's where I have to tell you about what I think is the most interesting idea I've ever had. And I say that as someone who has had a few. The year is 1993. I'm working on this with two colleagues, Lior Thorlasius and John Uglum, and we write a paper called Black Hole Complementarity. The key question was this: what actually happens to the information that falls into a black hole? And the answer I came up with was, and I want you to really listen to this, both things happen, and neither one contradicts the other. Let me explain. Imagine you're standing outside a black hole and your friend, let's call him Bob, decides to jump in, brave guy. From your perspective, standing outside, Bob approaches the horizon, slows down, gets redder, appears to freeze. And here's the thing we realized. From your perspective, the information that makes up Bob doesn't just disappear. It gets spread out across the horizon of the black hole, stretched and scrambled across this two-dimensional surface. It's there, it's encoded in the Hawking radiation that slowly leaks out. The information survives, quantum mechanics is saved. From Bob's perspective, he crosses the horizon smoothly, doesn't feel a thing, and according to everything he experiences, his information, goes into the interior of the black hole. He's there inside, intact. Both things are true simultaneously now. I know what you're thinking. That's impossible. How can Bob be both on the horizon and inside the black hole? That sounds like he's in two places at once. That sounds like a paradox. And here's the key insight. The punchline of the whole thing: you can never catch the contradiction. No single observer can ever see both copies of Bob. The outside observer sees the information come back out in the Hawking radiation. Bob himself experiences going in, but there's no observer. There can be no observer who sees both. Because to see the copy that came back out in the radiation and to see Bob inside the black hole, you would have to cross the horizon yourself. And once you cross the horizon, you can never send a signal back out to tell anyone about it. The universe has arranged itself so that the paradox can never be demonstrated. That's complementarity. It's not that both descriptions are simultaneously true in some simple sense. It's that both descriptions are valid from their respective perspectives, and the structure of space-time guarantees they can never be confronted against each other. Now, there's a beautiful analogy here that I love, and forgive me, but it comes from plumbing. My father was a plumber, and I think about these things in practical terms. Imagine you're looking at a pipe from two different directions, and from one end it looks like a circle, from the side it looks like a rectangle, you might say. That can't be the same object. A circle and a rectangle are completely different shapes, but they're both correct descriptions. They're just different perspectives on the same pipe. You can't simultaneously look at both ends and the side. The geometry prevents it. That's complementarity. It's multiple valid descriptions, each perfectly consistent from its own perspective, with the geometry of the situation preventing any contradiction. But here's the really deep thing I want to tell you, and this connects to my other great obsession, information and holography. And the outside observer sees all of Bob's information encoded on a two-dimensional surface, the horizon, not inside the three-dimensional volume of the black hole on the surface. And when I started thinking hard about that in 1994, when I wrote a paper called The World as a Hologram, I realized this wasn't just a curiosity about black holes. And so it was telling us something profound about the nature of reality itself. Here's the wild claim. The three-dimensional world you experience, all of it might be completely and exactly described by information living on a two-dimensional surface. It's like a hologram where a flat piece of film contains all the information needed to reconstruct a three-dimensional image, the holographic principle. And the reason I think the reason is that black holes give us a limit on how much information can fit in any region of space. And that limit is not proportional to the volume of the region. And since it's proportional to the surface area, nature is telling us something. Reality is, in some deep sense, two-dimensional, and the third dimension might be, in some way we don't fully understand yet, emergent, derived, not fundamental. Now, I have to be honest with you, this is still not completely understood. I don't want to oversell it. The holographic principle is on extremely solid ground. ADS-CFT, Juan Maldaceno's incredible discovery in 1997, which followed directly from the ideas I'm describing, made it mathematically precise in certain spacetimes. But whether it applies to our actual universe, our accelerating, expanding cosmos, that's where things get much harder. And that's actually what I'm working on right now. But I'm getting ahead of myself. Let me tell you about the war. When we published the complementarity paper in 1993, Hawking didn't exactly send me flowers. To be fair to Stephen, he was extraordinarily smart and extraordinarily stubborn, which is a combination that in physics can be either magnificent or catastrophic, depending on whether you're right. In this case, I think the stubbornness worked against him. His response basically was, "Nice try, but you haven't actually shown me how the information gets out. And you've told me that it can get out without contradiction, but you haven't shown me the mechanism." And that's fair. That was a legitimate objection. I had shown that complementarity was consistent. I hadn't proven that information actually escapes. So for years, the debate continued at conferences, in papers, in hallways. I remember being at conferences where people would take sides, and there were rooms full of brilliant physicists, people who dedicated their careers to quantum field theory and general relativity, genuinely, sincerely disagreeing about something as fundamental as whether information can be destroyed. It was glorious, actually. That's what physics looks like when it's working. Now, Hawking had a very specific intuition, and I want to give it its due, because it wasn't stupid. His intuition was that the interior of a black hole is genuinely disconnected from the exterior, and that once something crosses the horizon, it's gone into a different region of space-time, a region that eventually, when the black hole evaporates, simply ceases to exist. And he felt that the mathematics of general relativity strongly supported this. My intuition was equally strong in the other direction. I kept thinking, quantum mechanics is the most successful theory in the history of physics. Its predictions have been tested to absurd precision, and the idea that it just fails for black holes, not in some subtle, complicated way, but in the most catastrophic way possible, with information destruction that seemed to me like throwing out everything we know about physics. One of us had to be wrong about something deep. The turning point came in stages. In the late 1990s, Juan Maldaceno's AD-CFT correspondence essentially proved, in a precise mathematical setting, that quantum gravity is dual to an ordinary quantum field theory. And ordinary quantum field theory conserves information. Period. It's built into the mathematics. So in those spacetimes, anti-de Sitter spacetimes, which are slightly different from our universe, but close enough to reason about, information cannot be destroyed. The math just doesn't allow it. And Hawking held on, he always held on. But eventually, in 2004, at a conference called GR17 in Dublin, He stood up and publicly conceded. He admitted that information is not destroyed. And he said he had been wrong. I have to say, and I mean this sincerely, that was one of the great moments in the history of physics, not because I won, but because Stephen was willing to change his mind based on the evidence. That's what science is supposed to look like. And it took him 23 years from that dinner party in 1981 to get there, but he got there. But here's the thing. Even after Hawking conceded, the problem wasn't solved. And so we knew information had to escape. We didn't fully understand how. And then in 2012, a new grenade was thrown into the room. A group of physicists, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, wrote a paper that became known as the AMPS paper, or the firewall paper. And what they argued was devastating to complementarity. They said, wait a minute, and if information really does escape from the black hole and the Hawking radiation, then those escaping particles have to be entangled with the stuff that fell in. That's the only way information can be preserved, through quantum entanglement. But quantum mechanics also says that entanglement is monogamous. A particle can only be maximally entangled with one other particle or system. And so if the late Hawking radiation is entangled with the early Hawking radiation, which it has to be to carry out the information, then it cannot also be entangled with the stuff behind the horizon. And if it's not entangled with the stuff behind the horizon isn't smooth anymore. It's a wall of fire, a firewall. Anyone falling in would be instantly incinerated at the horizon. Its complement would be dead. I gotta say, AMPS was a beautiful argument. I spent a long time staring at it. My response, and I worked on this for years, is that the firewall argument, while technically correct in a limited sense, misses something crucial. The complexity, and the question isn't just about entanglement. It's about how hard it is to actually demonstrate that entanglement. And it turns out for a black hole that forms from collapse, the computational complexity of constructing a firewall is so stupendously enormous that it's effectively impossible. And the universe doesn't have enough time. But I'm going to be honest with you, the firewall debate is not fully resolved. We're still arguing about it. And anyone who tells you they've got a complete, clean solution is probably oversimplifying. So where does all this leave us? Here's the current state of play as I understand it. First, information is not destroyed. I'm confident of this. The math is too strong. ADS-CFT is too precise. The universe conserves information. Second, the holographic principle is real. And the three-dimensional description and the two-dimensional description are equivalent. That's not speculation. And that's been mathematically demonstrated in specific settings, and I believe it's a general truth. Third, there's a deep connection between quantum entanglement and the geometry of space-time. This is the ER-EPR conjecture, which Juan and I wrote in 2013, the idea that an Einstein-Rosen bridge, a wormhole, is entanglement. Not just related to entanglement, is entanglement. And two entangled particles are connected by a geometric structure, a wormhole, through space. Now, this sounds absolutely crazy. I know I was there when we thought of it, and I thought it was crazy. But think about what it means. It means that space, the geometric fabric of the universe, is built out of entanglement. Space-time emerges from quantum information, and the connectivity of space is a consequence of the entanglement structure of the quantum state. That's the frontier. That's where the real action is right now. My students and I, particularly Adam Brown and Henry Lin, have been developing a related set of ideas around computational complexity. Here's the question. The interior of a black hole keeps growing. And long after the black hole reaches its maximum entropy, long after it's done thermally, scrambling everything, the interior keeps getting bigger. What's happening? And my answer is that the interior is getting more complex. The quantum state of the black hole, as seen from outside, keeps increasing in complexity. Hence, we wrote a paper called Complexity Equals Action. The computational complexity of the holographic state equals the action of a geometric region we call the Wheeler-DeWitt patch. And black holes are the fastest computers in nature, and then there's what we call the second law of quantum complexity. Complexity always increases just like entropy. And it's a new kind of thermodynamic law for quantum information. And most recently, we've been pushing into de Sitter space, the geometry of our actual universe, which is accelerating. That turns out to be incredibly hard. I've written papers arguing that quantum gravity in de Sitter space might be impossible in certain formulations, or at least faces fundamental obstacles that don't exist in anti-de Sitter space. That's very much an open problem, and I think about it constantly, actually. You know what I think the deepest open question is? It's the one that connects all of this. And how does space-time emerge from quantum information? We have pieces of the answer. ER-EPR gives us a piece. Holography gives us a piece. Complexity gives us a piece, but we don't have the full picture. And we don't have the theory that starts from a quantum system with no geometry and shows you geometry emerging. Honestly, that might be the deepest problem in physics. And it's deeper than any specific question about black holes. I've been doing physics for more than 50 years now. 50 years I grew up in the South Bronx. My father was a plumber, and he used to tell me, "You ain't going to be no engineer. You're going to be Einstein." I think he was joking mostly. But here's something I've learned after all these years of doing this, something that I think is worth more than any specific result. And the things that seem most obviously true in physics are almost always the things most worth questioning. And when Stephen stood up at that dinner party in 1981 and said, "Information is destroyed," everyone nodded. It seemed obvious. Of course it's destroyed. It went into a black hole. What did you expect? And the hard part, the part that takes decades, is not finding the right answer. It's figuring out which obvious-seeming thing is wrong, which assumption you've been making without even knowing it. In the case of black holes, the wrong assumption was that information has a single definite location. And we assumed that if something fell behind the horizon, it was there, inside, and not also out here, encoded in the radiation. Complementarity says that's a false dichotomy. And the information doesn't have a single location. It has multiple complementary descriptions, and the geometry of space-time makes sure you can never catch it contradicting itself. That's the kind of thing that takes 28 years to understand, not because the math is so hard, though it is, but because you have to unlearn something you never even knew you'd learn. I'm 85 years old. I've still got things I'm working on, problems I lie awake thinking about the connection between black holes and de Sitter space, and it's the emergence of geometry from entanglement, the question of why this vacuum, out of all the 10 to the 500 possibilities, is the one we find ourselves in. I don't know if I'll live to see those answers, and you know what? That's fine. The universe doesn't owe us answers, but it does apparently reward persistence. My father wanted me to fix pipes. Instead, I've spent my life trying to understand what pipes and people and the planets and black holes and the entire cosmos actually are at the deepest level. And what they're made of, how they work, what rules they obey, I still don't fully know. Neither does anyone else. But I can tell you this, the answer is stranger than you think, stranger than I think. And that's what makes it worth getting up in the morning. And if what I told you about information and complementarity got you thinking, I want you to watch my next video where I explain ER-EPR, the idea that wormholes and quantum entanglement are the same thing, because that's where this story goes next, and I promise you it's going to blow your mind even further. I'll see you there.